For our project, we wanted to work on creating a controller for a Ballbot. We wanted to compare multiple controllers on the same plant in order to get a better understanding for each controller. We tested 4 different controllers on the Ballbot: an LQR controller, a dynamic programming approach, a trajectory optimizer, and MPC. And then we evaluated the pros and cons of each.
A Ballbot is a kind of robot that bounces on top of a ball, and by tilting around on top, they can move around. They're really cool because they take up a smaller footprint than normal wheeled robots and can tilt, while normal wheeled robots can't. They're also inherently unstable, leading to some rich dynamics that we're investigating here. Ballbots that you'd see in the real world exist in 3D, but for our project, we chose to work with a 2D one that just lives in the plane. This lets us tweak controllers faster because our state space is smaller, but it keeps the nonlinear dynamics for us to work with.
In order to control a Ballbot, we developed 3 methods of control. First, Jorge created a neural network that, once trained, could approximate the cost-to-go function and incorporated this in a dynamic programming approach. Second, I used Drake's mathematical program with various sets of constraints to develop a trajectory optimizer. And third, Fischer used this trajectory optimization code as a base for model predictive control to iteratively choose actuation values at every time step. We also used an implementation of LQR from the textbook as a baseline.
To provide a fair comparison between each of our controllers, we used a cost function to compare their performance. Since one of our controllers was LQR, it seemed natural to borrow its cost function to evaluate the performance of the other controllers. By using the LQR controller as our benchmark, we tried to come up with a controller that could have a lower total cost. If we could find one, we'd have beaten LQR.
For the LQR controller, we linearized the system around this top unstable point and created the controller around there. We found this controller easy to implement and surprisingly robust, even at extreme starting angles. We wanted to check the robustness of the LQR plant, so we tried the same controller parameters at 3 different starting points and with 3 slightly different plants for a total of 9 configurations. To approximate modeling error, we tried a standard ball, one with a ball with 20% heavier than expected, and another with a ball that was 20% smaller than expected. In all 3 cases, the controller performed spectacularly. We then tried a dynamic programming approach in order to find a value function. We used a neural net and randomly sampled from the state space in order to train the neural net. We discretized the action space using a small step size to find the next state. Through this process, we found that tuning the neural net hyperparameters in order to best estimate the value function was quite difficult. After hundreds of iterations, we finally found a half-decent result. However, it still underperformed in every case when compared to LQR. It still was stable, however, and did stabilize the plant to the original goal state.
In order to best compare trajectory optimization to LQR, we had to incorporate the same cost function and limit the number of constraints we put on the program. Once we did this, we noticed that given the same initial state, the trajectory optimizer would make some strange decisions about the Ballbot's behavior, sometimes skyrocketing actuation, even though this was being penalized. Eventually, we realized that this was due to the time constraint. Since we forced the controller to get to the goal state very quickly, the optimizer had to come up with some interesting and unintuitive trajectories. Once we gave it more time, the trajectory started to follow that of LQR, and once we removed the constraint of being strictly at the goal point altogether, it got even closer to the LQR results. So the takeaway here is that trajectory optimization will provide you with an optimal result. It can just be difficult to adjust the parameters such that you get something that you feel is optimal.
We wanted to take some of the same intuition about hyperparameters we gained from the trajectory optimizer and see how that played out in MPC. First, we tried a 2-second horizon where at every time step we asked the solver to take us to the goal within 2 seconds. Instead of producing crazy trajectories like we saw in the optimization case, it ended up just taking really small steps and not really going anywhere. So we tried to help our solver out by asking it to instead just give us the best trajectory over a 5-second horizon. We didn't constrain it to arrive at the goal, but this ended up working out well and gave us solutions that look similar to the LQR solution. Lastly, we tried to converge faster by reducing the horizon to 2 seconds while leaving the end state unconstrained. This actually converged a whole second faster than the trajectory optimizer, which was really cool,